Welcome to this video about free fall. This goes along with activity 5.1 for physical science. A few things about this topic before we get into a demonstration, and we then talk about solving some problems. When we are talking about free fall, we are talking about objects that are falling with a constant acceleration, so there is no air resistance. So again, objects are falling with a constant acceleration. Which means that there is no air resistance. Now this is important because in the last unit we've been talking a lot about friction. In free fall there is no friction. Okay. Now what is this acceleration? Well, here on Earth the acceleration is the acceleration due to gravity. So it will be 9.8 meters per second squared. Now most of the time you can approximate this to be 10 meters per second squared, but you do want to keep in mind that it really is actually 9.8 meters per second squared. A key thing about free fall also is we're not really learning any new math here. You already know all of these things that we're going to be doing. So we're talking about the kinematics equations that we learned early on. And they work, they all work. The only thing now is that rather than thinking about it in terms of x's, so rather than thinking about it in terms of objects moving left and right, we are now thinking about it in terms of the y, because objects are going up and down. So for example, if we want to talk about the equation that x equals v naught t plus 1/2 at squared, we now want to, instead of thinking about it as an x distance or displacement, we now want to talk about it as a y equals v naught t plus 1/2 at squared. Okay, so that's the only difference, and it's just a subtle difference here. It just allows us to keep in mind that we are talking about objects going in the y direction instead of in the x direction. One thing that may make this a little bit trickier for some of you is whether or not you know the quadratic formula and how to use it. So we will come back to that in a minute as well. What I want to do now is I want to take a look at a slow-mo simulation of an object falling in free fall and looking at some graphs that are associated with it so we can figure out what is actually happening. So in this situation, we have this object on the left-hand side here, this blue dot, and we are going to let it fall. As you can see, if you look carefully at the screen here, it is starting at 20-meter mark, and it is going to fall, and it's going to fall at a position of 0. So we can have it go to the left or go to the right, but we're not going to because there's no air resistance here, so there's no reason for it to change its path. It's just going to go straight down. Now on the right-hand side, you'll notice that we have a series of 3 different graphs. We have a graph of position versus time, velocity versus time, and acceleration versus time. You know how to get from one to the other already. Remember, going from position to time to a velocity per time, you would have to find the slope. And then to go from velocity to acceleration, you would again have to find the slope. And we can figure out a lot of information about that. So let's take a look. Let's go ahead and hit play. And you'll notice that the object is falling and it's making a motion map here on the left. It is a vertical motion map because the motion is in the vertical direction. So when we take a look at this, we can notice that it travels a small distance at first, and then it's increasing, all the way down till in the last bit of time here, it goes from the 4 meter, a little below the 4 meter mark, all the way to 0 very quickly. If we look at our graphs, we notice a few things. Number one, position versus time is a part of a parabola. So the slope increases in the negative direction as time goes on. Velocity versus time is a straight diagonal line. The reason for this is because this is free fall. It is under a constant acceleration, which means that the velocity will change at a constant rate. And if we look carefully here, it starts at 0 and it goes down to a negative 20 in 2 seconds. It goes down to a negative 20 meters per second. Now so if we get the slope of position versus time, we would end up with our velocity versus time. If we get the slope of our velocity versus time, notice that we get an acceleration curve here, and it is a constant minus 10 meters per second squared, because gravity on Earth can be considered to be 10 meters per second squared. It is minus because it is going down, and we make the assumption that our downward is a negative direction. Now I can change this. What if our acceleration on Earth, let's say that our acceleration is about 5, okay? Then we can see that it falls at a much slower rate. Its velocity time, position time graphs are very, very long. You can see the scale changing as we go through this. Where it only took about 2 seconds to fall last time, it seems to have taken about 2.8 seconds to fall this time. But the shape is still the same, and notice that the position still increases over time. Now our acceleration is only minus 5 instead of minus 10, which changes the slope of everything. What if there was a higher acceleration? What if the acceleration was about 15 instead? Now, because the force of gravity is larger, it's going to accelerate faster, so it's going to hit the ground faster. And in this case, it hits the ground a little bit after 1.6 seconds. Same pattern in the motion map, which means the same motion is occurring. It's just at different rates due to the different amounts of acceleration that's going on. So let's take a look at this and let's reset it back to the original Earth values. And let's talk about what's actually going on here so that we can get some numbers down and you can see how this all works. So I'm going to play this one more time. And there it goes, dropping very rapidly. And it lands on the ground at 2 seconds. So if I were to make a quick picture of what we were just seeing, we had the ball start here. And then as it fell, it got farther and farther away from where it was before at a constant rate. Now, if we were to set up a speedometer with this to see what was going on with it, and we wanted to figure out what was happening, and if we use the data from the earlier part of the video where we had the object falling in the simulation there, so at t equals 0 seconds, we are saying that its speed is 0 meters per second. And it has not dropped anywhere. So its y displacement is 0 meters. Okay, so now let's look at this dot here. Let's say that 1 second has gone by. If 1 second has gone by, how far has it fallen? And how fast is it going? Well, we can keep in mind that we know that we have the equation v final equals v initial plus at. In this case, we have 0 for an initial velocity, and our acceleration is due to gravity only because it's in free fall. So our velocity can be found by simply using the equation gt. So g is 10, t is 1. So our speed here is 10 meters per second. I'm going to call that V1 because that is our speed at the first second. So then the question becomes, well, how far did it fall? What was Y1? Well, we can do this a couple of different ways. We can say, well, we can find the average velocity and multiply it by its time and get the distance, but I would prefer to think about it in terms of that equation that we talked about on the last slide, where Y1 is equal to V naught T plus 1/2 AT squared. Again, V naught T is 0 because V naught is 0. A is gravity, and then we have T squared. So we have 1/2 times 10 times 1 squared. Don't forget to square your time, okay? This is a trap that lots of people get stuck in. So this turns out to be 5 meters. So the ball is now getting a speed of 10 meters per second and has traveled 5 meters. Let's jump down for a minute and let's see what happens. Let's say that the ball gets to here at t equals 4 seconds. I still want to know how fast is it going, and I still want to know where is it. So I'm going to do the same thing, except I can cheat a little bit now because I know that v is simply gt and y is simply 1/2 gt squared. So v4 is going to be 10 times the time of 4, which is 40 meters per second. And y4 is going to be 1/2 gt squared, which is 1/2 times 10 times 4 squared. And again, don't forget to square the 4. So we have 5 times 16, which if we multiply that out, we get 80 meters. So it has fallen considerably. In the first second, it only falls 5 meters, but in the first 4 seconds, it falls 80 meters. So we can use the same kinematics equations we've had before to go ahead and solve free fall equations. What happens, though, if we have a situation where the initial velocity is not 0? Let's take a look at that. So now let's say that we have the initial velocity is not equal to 0, okay, meaning that it's been thrown. Let's say that a ball is thrown downwards with an initial velocity of 3 meters per second. How long is it going to take this ball to fall 30 meters? Well, let's take a look. What do we know? We know its initial velocity is 3 meters per second. We know its acceleration is 9.8 or 10 meters per second squared. We know that it fell a distance of 30 meters. What are we looking for? We're looking for how long it will take. So we're looking for time. So if I think about the equations, then I know that I want to use that y is equal to v naught t plus 1/2 at squared. So if I plug in my numbers at this point, I get 30 is equal to 3t plus 1/2 times 10 t squared. I can simplify that to be 30 is equal to 3t plus 5t squared. Now at this point, I have a quadratic equation. And in order to solve a quadratic equation, we either need to be able to factor it, or we need to be able to use the quadratic formula. Let's use the quadratic formula because it's quicker and easier to solve most physics problems using that rather than trying to factor. So I'm going to rearrange this slightly so it's in a better looking format, and I'm going to say that it is 5t squared plus 3t minus 30 is equal to 0. Now the quadratic equation, remember, says that if you have a quadratic system like that, then you can solve it. So if you have ax squared plus bx plus c equals 0, then it says that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. If you do not know this, or you have not really fully mastered that yet, then let me know and I will give you some more practice problems on this. So if this is the generalized form of it and we look at our specific, then I'm not really solving for x, instead I'm solving for t. So t is equal to a negative b, so negative 3 plus or minus the square root of b squared, which would be 3 squared, minus 4 times 5 times negative 30. I have to put the negative in there because it is minus 30. All over 2 times a. So we get negative 3 plus or minus the square root of 9. 4 times 5 is 20. 20 times 30 is going to be 600. And there's 2 minuses, so it's a plus. So plus 600 over 10. Okay, so that gives me a negative 3 plus or minus the square root of 609 over 10. Square root of 609 is not something that I know off the top of my head, but I can find out that the square root of 609 is 24.68. Okay, so this gives me two possible answers here. I have negative 3 plus 24.68 over 10, or I have negative 3 minus 24.68 over 10. This bottom one cannot possibly be the answer because it gives us a t less than 0, and that's not possible. So we know automatically we can get rid of that one. When we get rid of that one and we solve for the top one, what we end up with is 2.17. So in 2.17 seconds, this ball will hit the ground. Okay, so again, one more time. We've thrown a ball downwards. It has an initial velocity. It has an acceleration of gravitational acceleration of 10. We want to know how long it's going to take to go 30 meters. We start with our y equation. We plug in our numbers, and then we have to use our quadratic equation here to solve it. Okay, let's do one more quick example. This time we're going to throw the ball upwards. So a ball is thrown upward. With an initial speed of 15 meters per second. The question is, when does the ball pass a point 8 meters above the person's head? Well, if we think about this for a minute, here's our person. They throw a ball upwards, okay? the ball starts to go up, and then it's going to come back down again. Okay. The question is, when does it reach 8 meters above the head? At t equals what? Well, let's write down what we know. Okay, we're going to make the assumption that at t equals 0, then the initial velocity is 15 meters per second. And we are also going to make the assumption that because we're in free fall, this is still in free fall, so the acceleration is 9.8, or again 10 meters per second squared. But here comes a new addition to this. Because you're throwing it upwards, notice that the initial velocity is positive. Acceleration is downward, so the acceleration is actually negative. Okay, so the acceleration is negative because it's pulling the object towards the ground. All right. What else do we know? We know that we want it to go to a height of 8 meters. And although we know the beginning conditions, when time equals 0, it starts with that velocity, we are trying to figure out when this occurs. So we need to now say, well, what is the time at that point? We're going to use the same equation we did before. But in this case, I'm going to change it again to be y. And we're going to say y is equal to v naught t plus 1/2 at squared. Now we can certainly say, whoa, wait a minute. This person is throwing it. So it has an initial height, doesn't it? Because it's being thrown upwards. Theoretically it could, yeah, because it is, if we go from a height here, then we're going to say, well, what about that part there? We can put our 0 point wherever we want. So in order to do that, I'm going to assume that the ball is actually not released until it is at the person's head. So in that case, I can say its initial height is 0, and we are going till the height is 8. And I can forget about the fact that the person even has the rest of his body. So when we do this, if I plug in our numbers, our y is going to be 8. Our v naught is 15. We have no idea what t is. Again, we have 1/2. But again, now we have acceleration, but it's negative 10 this time, times t squared. I'm going to rearrange this equation a bit, and I'm going to get everything to one side of the equation. So 1/2 times negative 10 is negative 5. If I move it over here, I get 5t squared. I'm going to move the 15t over, so minus 15t plus 8 equals 0. Again, quadratic equation. T is equal to a negative b. Well, a negative 15 makes it positive. So a negative b plus or minus the square root of b squared minus 4ac all over 2a. So again, one more time, this 15 here is positive at the beginning of the equation because it's a minus 15t in the equation. So we have 15 plus or minus the square root of 15 squared, which is 225, minus 5 times 4 is 20, 20 times 8 is 160, all over 10. 225 minus 160 is 65. So we have 15 plus or minus the square root of 65 over 10. We again will end up with two possible answers here. The square root of 65 is 8.06. So we have 15 plus 8.06 divided by 10. which gives us an answer of 2.3 seconds. Or we have 15 minus 8.06 over 10, which gives us 0.69 seconds. Well, how is this possible? How can we have t equal to both 2.3 and 6.9 seconds? In this case, it is possible because the ball is going up first and then down. So it's going to hit the 8 meters above the head twice, once on the way up at 0.69 seconds and once on the way down at 2.3 seconds. So in this situation and in this unit, the things that you have to keep in mind are you are definitely going to be using the kinematics equations that we have used before. And secondly, you have to remember that gravity is 10, and it could be positive or negative. And finally, you have to remember the quadratic equation. So let's just make that a quick list. Okay? Remember, 1, kinematics equations. 2, that acceleration is equal to gravity because it's free fall. Okay, this is super important. Now, if we get off the Earth, it will not be 10. It will have some other value, but it is still equal to gravity. And another thing about this is it can be positive or negative depending on the situation. In our second example, it was negative because we had an object going up in the positive direction and acceleration was down, so it had to be in the negative direction. You can look at it as always being negative, and then you have to make sure that your velocities are positive or negative. That's up to you if you want to do it that way. The third thing that you have to remember is for the quadratic equation, ax squared plus bx plus c is equal to 0. To solve that, we want to use that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Sometimes both of those answers will be valid, and sometimes they won't be. So that should be enough information to allow you to go ahead and do assignment 5.1. So, bye for now.